Hey, what's up? Welcome to the East Wing. In the East Wing, we're going to be taking a look at 3 calling conventions. Now, x86 actually has quite a few calling conventions, and what I think, and I'm not entirely positive, but it turns out that when x86 was really popular and 32-bit architectures were sort of like the new thing, the industry was booming. People were starting to buy computers and put them in their homes. Everybody had them. Lots of people were playing computer games and using them for work. There were lots of developers creating new tool chains and new compilers, and with that comes a lot of specific design decisions. Those design decisions sort of involve this contract between functions. So imagine I am calling a function that takes a name and an age. How do I represent or give that information to the function that I'm calling? Do I push them to the stack, and which order do I push them? Like in reverse order, in the normal order? Do I put them in registers and then call? But then registers are really precious. I only have a few of them. So maybe I don't want to do that. Maybe I put them somewhere else in memory. And then once I'm done, who's responsible for cleaning up the stack? Is it the function that was called or the calling function? This contract between the caller and the callee is what we consider the calling convention. There's a bunch of them, there are different names, but we're going to take a look at 3 common ones, and that's what we're going to see in the East Wing. Now, full disclosure, I really screwed this up when I wrote this because I intended for the user to have to really think about the calling convention that was used, and it turns out you don't at all. But we'll take a look at sort of like those defining characteristics and then end up just seeing what should have happened. All right, so let's take a look here. When we come into this, we'll go into the East Wing. Now, the East Wing says you enter the East Wing as if the entire room were carved from marble. You realize you're in a bank. You see a flashing keypad on one of the vault doors. Welcome to the North Pole Bank Head Elf Vault. Please enter PIN. All right, so in this case, we need to enter a valid PIN. If I just enter junk, it says an alarm sounds. The room fills with smoke. Red lasers scatter across the room and settle on your chest. You run in fear. So we go back. We still have 2 keys from the North and South Wing that we solved. Now we're going to keep going into the East Wing and see if we can solve this. Now, we'll see that when we go into the East Wing, we end up sort of like zooming out, and there's no like specifically interesting patterns. We sort of get this like semi-stair pattern where we have this check, and we'll either come over here or we'll bail out, or we'll come down here and bail out down here. So this is an if-else statement that's nested. So when we look at this, we have to like get past these 2 points before we get into this. So it's like 3 steps, right? This isn't the ladder form that we saw earlier. So in this particular case, what's going to happen is we're going to collect some information from the user, from this fgets, and we'll see that in each one of these. And then it's going to be passed in a very specific way to the function. The way that it is passed to the function ends up being characteristic of the calling convention, right? So normally what happens, and you think of like default or standard, the calling conventions that we're going to be looking at here are cdecl, standard call, and fast call. And in that particular case, what's going to happen is we're either going to pass all of the parameters onto the stack and then call the function, or we're going to pass some parameters into registers, the rest on the stack, and then call the function. The part where I messed up is that we take this information from fgets, we end up isolating those bytes, and then putting those bytes into different registers, and then putting them onto the stack, and then calling this. And then once we do that, I end up just basically blindly checking those characters, and that's it. It's done. There's no special thing that you have to think about or do, so it was an error on my part. So anyway, to solve this, we end up just coming down here. Again, this is an if ladder. And again, we have these if conditions and one specific failure case that we jump to, and then set here. So it turns out that like one case will set this to 1, or it'll end up failing and coming to 0. So when this function is called, it essentially has an integer or Boolean type, And what it's going to end up doing is returning 1 for success, meaning the pin code was right, or a 0 for a failure, meaning the pin code was wrong. So what we end up doing is displaying all of these as character constants to get the actual values that we need to type in. So we do 5, 7, 1, 8, and let's see if that works. 5, 7, 1, 8. And it says the vault door slides open with a hiss. Chunks of candy cane and whispers of children's giggles tumble from the door and the room beyond. You skip inside to notice a second, much larger door with a keypad. Please enter PIN. So now we have this process where we have to continue this. And this is not exciting or challenging at all. We just come in here, and then we set these as a character constant and get the rest of the values. But if we look closer, there's something interesting going on here, and we'll be able to focus on what's actually happening if we take a look at what happens before we call these. So first of all, in the first calling convention that actually happens, we pass a bunch of stuff onto the stack. In fact, every single thing is passed onto the stack. This particular function ends up taking 4 parameters. If we come in here, Binary Ninja has evaluated this and said, yeah, it looks like 4 arguments are actually passed to this. All of those are here, and they end up being pushed in reverse order. All right, so what we want to take a look at is the calling convention of the first call. So we'll call this door 1. I can give it that Z underscore thing. Come on, Binary Ninja. Let me go back into door 1. All right, sometimes when you name things, it seems to be an issue in the demo version. I don't really have that in the full version, at least that I've noticed. Maybe I'm wrong. So anyway, we have this concept where we take the parameters and we push them onto the stack. And we know that because this move is sort of like a push where we just basically insert it. This location on the stack we call door 1. Binary Ninja is able to discern that it has these 4 arguments, and these 4 arguments exist on the stack. We have this location here that's referenced, put into these registers, and then we take the low byte and then reference them and put them back onto the stack in a different location. This is kind of strange. Essentially what we're doing is just actually taking that same value and then clearing what else might be there and putting it in here. This is a compiler optimization or compiler decision. All right, so let's take a look at door 1. Actually, I'm going to name all of these right now, and we're going to do door 2 just so we know sort of like where we are in all of this. And then I'll go down here and name this one Z door 3, just because I know there happens to be 3 doors. All right, so in the first door, what we'll notice is that we take 4 parameters and we put 4 moves onto the stack before calling this. Now, commonly what happens is parameters are actually pushed to the stack, and then the function is called. And the parameters are typically pushed from the end or the last parameter to the forward one. So it's pushed from right to left. If you have a function that takes name, age, and gender, it's going to push gender, age, and name. It's going to push them in the opposite direction. So it's going to do that, and then it's going to call the function. The function is then going to know how many things to reference off the top of the stack, and then it's going to continue down and do whatever it does. At the end of that, there's going to end up being some cleanup or stack adjustment. And what's interesting here to note is that there's no cleanup or stack adjustment here. This is the caller function. It's the one that's calling this guy. This is the callee. It's the one that's been called. And at the very end, there's cleanup performed by that particular callee. In this guy, the caller didn't clean up anything. It didn't care, and it pushed all of its parameters onto the stack. This is indicative of standard call. So let's take a look at one resource that I talk about in the documentation. This is just a blog here, and there's X86 Calling Conventions. I'll put this in the descriptions here if you remind me. And one of the things here, it says stack cleanup is by the caller. It pushes all the parameters to the stack in reverse order from right to left. This sounds like cdecl. It sounds like cdecal because it hits all those characteristics. Standard call, we would think that it's standard call if it basically did all the same things, but the call E was responsible for it. So it looks like actually, this is standard call. So it's standard call because all the parameters are pushed onto the stack. We can hypothesize that it was in reverse order, and if we actually do some of the analysis looking at each individual instruction, we can see that that is in fact the case. And the call E ends up actually doing the call for this. So the call E is door 1. At the bottom, the stack is actually cleaned up. Perfect. This guy is standard call. Pretty sure. All right, let's go down and look at the next one. The next one, same thing. We have 4 parameters that are pushed to the stack. This guy is done down here. There's still some stack cleanup, but what happens is there's stack cleanup here as well. What's going on? So it turns out that this one is sort of indicative of cdecal. So cdecal is sort of the same thing where we have parameters are pushed to the stack. There's reverse order from right to left, but the caller is also responsible for responsible for cleaning up the stack. So we have this guy, which is showing that sort of stack adjustment here. So if we come back down, you see this guy, what we end up seeing is stack adjustment by the actual caller, and then a couple of parameters that are passed in, and then something else. So we have one argument that was passed in ECX, it says, and then this particular one was passed in EDX, and then we have these two which were passed by the stack. This one says standard call, but standard call doesn't actually have this convention. So it turns out this particular guess appears to be wrong based on what we know. So if we look at some of the calling conventions and the characteristics of this, it turns out that fast call will push or pass the first 2 parameters in registers, and the rest will be on the stack in reverse order. Not only that, the call E, or the actual function that was called, is responsible for cleaning up the stack. So down here, the stack cleanup should be maintained by the actual call E. There's a weird thing that I should have done, which is actually setting up this specific stack alignment. This is really confusing because in this particular case, it looks as if the information for this particular call, which is fast call, is being handled by the caller. This is really unfortunate because it turns out that there is a specific stack alignment that's dictated by the ABI, this application binary interface. I talk about it a little bit in this particular blog post. As a matter of fact, when we compile all of the sample code for all of this to take a look at analyzing these, we end up doing this M preferred stack boundary 2 to tell GCC that we want a specific 4-byte alignment rather than what the API dictated 16-byte stack alignment is. So in other words, this is just a disaster of a problem for teaching this particular concept. Not only do we have to really think about the calling convention when we do these comparisons and try to understand what the values are that we're typing into this. That was a major failure. And also there's this kind of like odd thing where we see the stack adjustment in here, and then we also see the stack adjustment in here, and it's like, what the heck is actually going on? What I can say is that it ends up being this really weird case where there's a different stack alignment. There's this sort of like mercy space that ends up being put on the stack, and we can actually redefine that or tell the compiler not to do that stuff. So there's certain things that'll happen that'll kind of throw off the scent of like what's happening. It turns out this idea of like who's responsible for cleaning up the stack can be confusing based on what the actual stack alignment ends up being for the compiler or the compiler settings. So in this case, what we're able to just see, and in so many words, is that there was one cdecal, one standard call, and one fast call. The fast call was the one that used the 2 registers. If we come down here and kind of read what's going on here, it'll talk about which particular registers are actually used. And in here, we can actually see sort of this example where there's this print favorite numbers, and this takes 3 parameters. And each one of these, like the first 2, are actually set by ECX and EDX. If we go into our case, we see that ECX is actually set, and then inside of here it says also EDX is the second one too. Which is funny, it was able to actually discern that all of the stuff that's in here is correct, but it says it was standard call. That is not a standard call calling convention, so this unfortunately is incorrect. We can type Y, and then I believe here we can actually like make that adjustment and just say that it's fast call. It doesn't necessarily matter too much in this particular case. It was really just to try to teach a concept. Unfortunately, I think I did a really bad job, and this particular blog post that I've written in the past, I think does a much better job of illustrating the types of characteristics that you'll see, because it ends up compiling with certain flags and showing a little bit more directly what that concept is. So the bottom line is it's really important to understand that when we call functions, we're really interested in a lot of cases what the arguments to those functions are, and it depends on what calling convention is actually being used. And it's something that is sort of the domain or the responsibility of the compiler to decide. You can actually override this, which is what we ended up doing. So we're north, south, east wing. If I come in here, when I set up these particular functions, I'm doing this attribute cdecl, an attribute standard call, an attribute fast call. That's what's actually determining or overriding the sort of general sense. And this is actually not needed because cdecl ends up being the default calling convention. So cdecl ends up being the default calling convention for a lot of compilers, including GCC, which is also MinGW that we end up using here. So you'll end up seeing cdecl quite a bit, and it turns out that on different operating systems for different APIs, they'll sort of favor one particular calling convention over another and standardize things on one versus the other. In most cases, you'll never need to or want to set a specific calling convention unless you're doing really funky things like sort of like defining a function or calling a function by a pointer, or doing something really funky where you're modifying values in inline assembly before calling a function, and you need to make sure that things get pushed in the right order for the specific calling convention that's used. Really, this is just important to sort of understanding how parameters get called or passed into functions. So hopefully this was somewhat helpful. I realize it's not the best example of how to go through this, but hopefully you'll read the blog post and then go through this example, and it'll be a little clear. We'll see you in the next wing, which is significantly better than this one.